Okay, so we're going to start notes on section 6.8, which is on roots and zeros. So I'm not going to go through the warm-up. The warm-up equation's up here, and we're going to go through the first key concept from this section. So all three of these statements that I'm going to write are all equivalent, which means they all mean the same thing. And so before I get started, I'm going to write the answers that we got for the warm-up equation. So the answers to the warm-up were x equals plus and minus 2i, and plus and minus the square root of 2, which means that those are all roots of the equation. So these three statements are all going to be the same thing. So we can say that the square root of 2 is a 0 of f of x. Another way we can say the same thing is to say that x minus the square root of 2 is a factor of f of x. And the last way to say the same thing is that the square root of 2 is a root or solution to f of x equaling 0. So those are three different ways to say the same thing. So if we know that x equals the square root of 2, we can say that that's a 0 of the function, which means that it's a 0 or an x-intercept. We can also then say that that has to create the factor x minus the square root of 2. Because if you think about it, we have x equaling the square root of 2, and we solve for x by setting it equal to 0. So if we undo that, we get x minus the square root of 2 equals 0. So that's why the factor is that. And then another way to say that is the square root of 2 is a root or solution to the equation being equal to 0. Pretty basic. We've been using that wording all year. We're just making it more formal at this point. The next thing that we're going to learn, and this is really key, this is the fundamental theorem of algebra. Fundamental meaning that it's super duper important. So what this theorem says is that every polynomial with degree greater than or equal to 0, which means that there has to be at least one x in the equation, has at least one 0 in the complex numbers. I'm going to abbreviate numbers. So remember, complex numbers, it's probably been a while since we've talked about these and since you've learned about like your number systems, but complex numbers are real numbers and imaginary numbers. So complex numbers deal with every type of number there is. So they can be rational, irrational, terminating, non-terminating, repeating decimals, imaginary numbers, so things with I in them, whole numbers, negative numbers, all that good stuff. Those are all complex numbers. And then we have this corollary, and a corollary in math just means an additional part. So like the theorem is like the big overarching rule, and then the corollary is normally something smaller that is a result of the bigger thing. So this was proved later on, and that says that every polynomial with degree n has exactly n roots in the set of complex numbers, or just in the complex numbers. So originally they proved that every polynomial has at least one solution in the complex numbers. So they have at least one answer if you set it equal to 0. And then later on, they proved that every polynomial with degree n also has n roots. So like if I have a fifth degree polynomial, a quintic polynomial, I have to have 5 roots. And they can be real numbers or imaginary numbers, but there are 5 solutions. And this is stuff that we've been talking about in class. We're just formalizing it now by going through the definitions. So the big thing for this section is, well, after we solve this, we're going to practice solving this, and then we'll get into the big thing. So just to show, right, we have a degree 2, which means we have 2 solutions, 2 roots. Right, so if we wanted to solve this, we could solve it by factoring first, right? We could see if we could factor it. So AC would give us negative 16, B would be negative 8. Sorry, this is positive 16. So 2 numbers that multiply to positive 16 but add to negative 8 would be negative 4 and negative 4. So that means this factors to x minus 4 times x minus 4 equals 0. But we know if something is multiplied by itself, that's the same thing as saying it's squared. So we can rewrite this as x minus 4 squared equals 0. So then to solve for x, I take the inside and set it equal to 0 and solve for x. I get x equals 4. And because it has this exponent of 2 up here, that's going to tell me that this has multiplicity 2. I didn't mean to stay on yellow, but I'm too far in, so we're going to keep with it. Actually, I might be able to change the color. Here we go. There we go. Now it's a little easier to see. So we would say x equals 4 with multiplicity of 2, or you can write this as, no, get off of yellow. Try this again. Or you can say x equals 4 is a double root, meaning it happens twice. Okay, so now on to the big thing. So this is Descartes' rule of signs, and that is pronounced Descartes. You don't pronounce the S's. So he is this major philosopher guy. He's come up with a bunch of stuff. You use one thing that he came up with all the time, right? The Cartesian plane is named after Descartes. He was also like a philosopher, so he came up with ways of thinking and all that good stuff. He's really interesting. If you're into history at all, you should definitely look into him. But he came up with this way of determining the types of solutions that a polynomial equation will have. And by types of solutions, we mean that they're going to be positive real solutions, negative real solutions, or imaginary solutions. So those are our 3 categories. So we're going to look into the number of positive real solutions, number of negative real solutions, and the number of imaginary solutions. Okay. Now, this stuff is going to maybe not make some sense when I write it out in words, but we're going to do some examples and then that should clarify it. So the number of positive real roots is equal to the number of sign changes in f of x, or is less than this number by 2. Right, and it's okay if that doesn't make sense. We're going to go over it in an example and show you what that means. The number of negative real roots is equal to the number of sign changes in f of negative x, which means we're going to plug negative x in and see what happens. And same thing, or is less than this by 2. And now imaginary is the easiest number to find. It's whatever's left. So whatever number of solutions is left to get to the total. Right, so like if you have a 3rd degree polynomial like cubic, you have to have 3 solutions. So you have to make sure that all 3 of these categories add up to 3. So we're going to go through an example. If you didn't quite get all of this written down in the same time frame, just pause the video and write it down and then go on. So we're going to do this first example, which, I lost my paper, hang on. Which in class I gave you a worksheet, so the first example is on there. So first example is going to be, we're going to find the possible number of imaginary and positive and negative real zeros for each function. So those are the directions, and we're going to work with this function first. F of x equals 2x cubed minus 5x squared minus 30x minus 24. Okay. So the first thing we're going to do is we're going to look at positive real. So to figure out how many possible positive real solutions you have, you look at your original function. So if we look here, we have a positive 2x out front, and then if we go from this term to this term, we go positive to negative. So we have one sign change, and then we go negative, negative. So it stayed the same, so that's not a sign change. Negative, negative, not a sign change. So we only have one possible positive real solution. And that means we have to have at least one. So because you can't reduce this number by 2, we have to have 1. So I'm going to write that out. So because we can't subtract 2, we must have exactly one positive real root. Okay, so now we're going to look at negative real. Okay, so for negative reals, we have to do f of negative x. So all that means is I'm going to take my problem and I'm going to plug negative x in everywhere I see x. So just like this. So then it's thinking about what's going to happen as we apply these different exponents to it. So if I cube a negative, my answer is also going to be negative. So I'm going to get negative 2x cubed here. If I square a negative, it's going to go back to being positive, so this term is going to stay the same. That negative 5 isn't going to change. Right? Negative 30 and negative x is going to give me positive 30x, and then nothing is affecting that 24, so it's going to stay negative. So then same thing here, we're going to look at our sign changes. So as we move negative, negative, right? No change. Negative, positive, we do have a change. Positive, negative, we have another change. So we could have two possibilities because we have two sign changes, or we can have no negative real solutions because you can decrease that number by 2. So you always count down by 2 basically. So then to figure out our imaginary solutions, we're actually going to set up a table to put together all of our possibilities. So scroll down so we can see everything. Okay. Or the board can keep scrolling, that's fine too. Okay, so we have our 3 categories. We have positive real, in which case we have to have one solution. We have negative real, where we could have 2 or 0, so we have to have both categories. And then we have imaginary and our total. So because this is cubic, we have to have 3. And now, because we have 2 possibilities for negative real, we know that this has to be 1. So in both cases, whether I have 2 negative real or 0 negative real solutions, I have to have 1 positive with it. So now if I look in my first row, I have 1 plus 2. I already have 3 solutions here, so I don't need any imaginary. But here I have 1 real solution with no negative real solutions, which means I have to have 2 imaginary solutions in order to get up to that 3. So these are our possibilities for answers. Now you might be thinking, why is this useful? Why are we learning this? So in today's technology world, you're right, this isn't very useful because we have graphing calculators, so we could always graph the equation and see exactly what our answers are. But in Descartes' day, when he came up with this, there was no such thing as a graphing calculator. You had to do everything by hand. And this is kind of cool because you can kind of see like what the possibilities for your answers are. And it's kind of neat to think about how they did math back before we had all this technology and that they came up with all this stuff without having a computer or a calculator with them. Oh, I'm an idiot. I forgot I put the problem in here. So we're just going to keep moving and pretend that didn't happen. Okay, so you would be assigned this as your OYO question, and it's the second problem on the worksheet in class. So if you are at home, just pause the video, try it out, and then I'm going to go through the answers. So pause it now because I'm going to start. Okay, so if we look at the original polynomial, we have positive to negative here, so we get 1 sign change, and then negative back to positive, so 1 sign change. So that means for my positive reals, I I can have 2 or 0 possible answers there. Now if I look at f of negative x, by plugging in my negative x, I'm going to get 2 times negative x to the 4th minus 13 times negative x squared plus 15. So if I apply a positive exponent to a negative, it becomes positive. So this is going to stay 2x to the 4th minus 13x squared plus 15 because I have all even exponents. So since the equation didn't change at all, that means my negative real solutions are also 2 or 0. So now we want to make sure we note that we have 4 total solutions. And then we're going to go ahead and set up our chart. So I have a column for positive real. So I can have 2 or 0 there. I have negative real, imaginary, and total. And I know what my total is. It has to be 4. Okay, so now we want to think of all the possible combinations. So I have 2 and 0 for my positive real. And then I have 2 different options here for negative real. So I could have 2 positive real solutions and 2 negative real solutions. I could have 0 positive real solutions and still get 2 negative real solutions, which means that I need to repeat my rows down because then I could have 2 positive real with 0 negative real, 2 positive real with 2 negative real. So I have to have all of my possible combinations of those values. And then it's just kind of looking to see, okay, how do I put them together to equal 4? So if I have 2 and 2, I already have 4. I need no imaginary solutions. I have 2 negative real. I could have 2 imaginary. 2 positive real, so I need 2 imaginary to fill it out. And then no real answers. I could have all 4 being imaginary solutions. Okay, so the closure question is, how could Descartes' rule of signs help you when you're solving a polynomial? So think about when we were solving all those big equations. You want to think about that answer and write it down. And then you also want to try and complete numbers 3 and 4 on the practice worksheet, which is posted on Schoology for you. And then you want to show me that for classwork credit.